Hello everyone and welcome back. Today we are going to return to the concept of null space, this time from the perspective of span and linear combination. So let's recall that the null space of a matrix are all of the vectors in the domain which become zero after they are multiplied by the matrix A. We've noted that there is one vector that is always in the null space of a matrix no matter what, and that is the zero vector of the domain. So the null space is never completely empty. The null space always contains at least one vector, namely the zero vector. But if you're in a situation where your matrix A has a larger null space than that, if there are other vectors that your matrix A destroys, then we can describe the null space of the matrix as a span of a finite set of vectors. And let me just demonstrate that process to you in the following example. It says, find the null space of the following matrix A, and we have 2, 1, 3, 0, 2, 4, 1, 1, 2. So because we're interested in the null space of the matrix, we're asking ourselves essentially what are the solutions to the matrix equation AX equals 0? So what I can do, I could take this question, currently expressed in the format of a matrix equation, and I can transform it into one of the other representations of this question. For example, it might be convenient, again, to take this question and represent it in terms of an augmented matrix, because when we represent this in terms of an augmented matrix, then we unlock the ability to do, for example, row reduction. So let me take the matrix A, 2, 1, 3, and augment it with the 0 vector on the right side. So 2, 1, 3 augmented with 0, 0, 2, 4 augmented with 0, 1, 1, 2 augmented with 0. So according to Wolfram Alpha, when we row reduce this matrix, in this particular case, the matrix on the left-hand side of the bar has become the identity matrix. It's got ones on the diagonal, and it's got zeros elsewhere. And of course, this column of zeros on the right-hand side remains zero, no matter what elementary row operations are performed. So let's go ahead now and interpret this result, and let's think about all the vectors in the domain that produce this output of zero. If I interpret each of these columns as standing for a particular coefficient on x1, x2, and x3, then this first row would mean x1 must be equal to 0, x2 must be equal to 0, and x3 must be equal to 0. So in this case, the matrix equation, what vectors become 0 after A is applied? This matrix equation has only the trivial solution. Only x equals the 0 vector is in the null space of A. So in this case, if someone asked me to find the null space, I could say, for example, that the null space is the set containing just the 0 vector. So this is an example of a matrix A that doesn't really destroy any information, that doesn't really compress or flatten any vectors as it acts upon those vectors. The null space in this case is just the trivial solution. Now, by contrast, let's consider the matrix A 1, 2, 3, 4, 5, 6, 7, 8, 9. And let's think about what is the null space of this matrix. Again, if we're asking what is the null space of this matrix, we're asking what vectors x become 0 after this matrix A is applied. What vectors are destroyed by the action of this matrix? Now, once again, I can go ahead and take this question and I can transform it into the equivalent question in one of the other formats that we've studied in this class. So, for example, as an augmented matrix, which will allow me to study the situation using row reduction. So let me go ahead once again and type this augmented matrix into Wolfram Alpha to see what it is after being row reduced. So in this case, when we row reduce this matrix augmented with the zero vector on the right-hand side, we end up with a row in the bottom containing only zeros. So in this situation, we've ended up with a free variable, which indicates that we do not have any unique solution. If I wanted to write down what this particular augmented matrix is telling me right now in terms of these solutions to the matrix equation, then this first line would say x1 minus x3 needs to be 0, and x1 plus 2x3 needs to be 0. But this third variable here, x3, is free. We started by asking the question in the format of a matrix vector product. We then took the question formatted in that language and we turned it into something in terms of an augmented matrix. And that allowed us to do row reduction. To help us to interpret the results of that augmented matrix, we turned those results into a language that's slightly more familiar to us, the language of systems of equations. Let me take this answer and translate it into the language of linear combination and span. If I take the equations in the system and I rewrite them, for example, in the format x1 is equal to x3, x2 is equal to negative 2x3, and x3 can be whatever it wants. Let me just say x3 is equal to itself. Notice that this allows me to take the vector x, the vector that has its first entry, its second entry, and its third entry, and express the entire x in terms of a single variable. The x1 has to be equal to x3, the x2 has to be equal to negative 2x3, and the x3 has to be equal to x3. So the entire solution, the entire vector x, in this case can be expressed in terms of the single free variable x3. And because x3 is present in all three entries, you can then factor out that x3 from all three entries. And you can write something like the vectors in the null space must be x3 times what's left behind after factoring out x3 from this vector. The number 1, the number 2, and the number 1 again. So any vector in the null space must have this form. Some number times this vector, 1, minus 2, and 1, which means that the null space of this particular matrix can be understood as the span of this vector. So to emphasize, the zero vector is always in the null space of every single matrix. However, certain matrices also have other non-zero vectors in the null space, and let's speak a little bit about the conditions that lead to having more than just the trivial solution in the null space. I want to point out, for example, that this particular matrix A is one that we studied yesterday. When we were talking yesterday about column space and we row reduced this coefficient matrix, we noticed that the column space was spanned by the first two columns of A, the first two columns being the pivot columns of the matrix, the location of pivots after the matrix was row reduced. And we observed yesterday that because our matrix was 3 by 3, it was taking three-dimensional vectors in the domain. But because the range of the matrix was spanned by only two vectors, the range of the matrix was a fundamentally two-dimensional object, similar to a plane in 3D space. So because A was taking a three-dimensional set of inputs and producing a two-dimensional set of outputs, we predicted that the null space of A would be one-dimensional. because this loss that's happening as we go from 3D onto 2D, this loss 3 minus 2 would be one dimension of information that A is compressing. And we have essentially verified that result here. In this case, we have the matrix A, and we were studying its null space. When we looked at all of the vectors in the domain which became 0, those vectors had the format of some number times this single vector, 1 minus 2, 1. So in this case, our null space was spanned by a single vector. So the null space is one-dimensional, as predicted. So these kinds of results of predicting the dimension of the null space and relating that to the dimension of the column space is sometimes referred to as the Rank-Nullity Theorem. And the Rank-Nullity Theorem says if you have a matrix A that has however many columns, the number of columns of A represents the dimension of the domain. If you then look at the rank of the matrix A, in other words, you count how many pivot columns A possesses, then this tells you the dimension of A's range. And if you calculate the difference between these two values, the number of columns minus the number of pivot columns, the dimension of the domain and the dimension of the range, that difference tells you how many dimensions of information are being lost or compressed by the action of the matrix. The difference between these two is going to tell you the dimension of A's null space. In other words, the number of columns of A that correspond to free variables in a system. For every column of A, the column is either a pivot column or it's a column corresponding to the free variable. The pivot columns are essential to understanding the column space. The free variable columns are essential to understanding the null space. So the columns of A kind of split into these two categories. Pivot columns talking about the column space and free columns talking about the null space. So this result is sometimes referred to as the rank-nullity theorem because it relates the rank of A, the number of pivot columns, to the null space of A and its dimension. Now, if you have studied the null space of a matrix, that can help you to express solution sets to other matrix equations involving that matrix A. So for example, let's return to this case of the matrix A being 1, 2, 3, 4, 5, 6, 7, 8, 9. And I would like to apply that matrix A to a vector and get the output -1, -1, -1 as the result. Let's try and describe all the vectors x that will serve as solutions to this system. Now, as usual, I can approach this problem by converting it to an augmented matrix. And then row reducing that matrix, for example, using technology. So here is this augmented matrix after it has been converted to reduced row echelon form. Let's now interpret what this augmented matrix is saying to us in terms of the solutions to this matrix equation. So the first row of this matrix would say something like x1 minus x3 equals 1. x2 plus 2x3 equals -1. And the variable x3, once again, is free because our coefficient matrix only has a rank of 2. So that leaves a free variable here. I can rewrite every component of the solution in terms of my free variable. I can say that x1 must be equal to 1 plus x3. I can say that x2 must be equal to minus 1 minus 2x3. And I can say that x3 must be equal to itself. So I can take the entire solution and I can express it as a combination of two vectors. A combination of the vector 1, minus 1, 0, corresponding to this 1, this minus 1, and this 0. And then combine that with whatever x3 is equal to times the coefficients here in the back, 1, minus 2, and 1. So now we can not only say that this system has infinite solutions, we can also describe the nature and the shape of all the infinite solutions to this system. System has infinite solutions. Specifically, all solutions have this form. Now, what I want to note about this equation right here is that it's very similar to the null space that we found earlier when we were working with this exact same coefficient matrix. When we were working with this coefficient matrix A and we were looking at the null space, the null space was equal to x3 times this vector 1, minus 2, and 1. And in this case, where we're trying to get an output of some non-zero vector b, the only difference is that we've gotten that same null space plus some other vector. So let's note that when solving this equation with a non-zero b on the right-hand side, what we got is the null space plus something else. This kind of formation, this kind of pattern, might be familiar to you if you have completed differential equations. In differential equations, one major segment of the class is devoted to solving what are called linear differential equations. And you start in differential equations solving equations that have a 0 on the right-hand side. And when you solve this equation, we write our solutions as a span. So we express solutions to this equation as a span of two functions. Now, if you're working on a differential equation that has something non-zero on the right-hand side, if you replace this 0 on the right-hand side with something else, then the solution to this equation with something non-zero on the right-hand side was related to the solution that we got when there was a 0 on the right-hand side. In particular, you find that the solution to this equation had the format of solve the equation with the 0 on the right side and then add one extra solution to it. So this formation that we're seeing up here, null space plus one other vector, is exactly the same formation when working on linear differential equations in a differential equations class. So in honor of the kind of language that's used in differential equations, homogeneous referring to an equation that's got a 0 on the right-hand side, non-homogeneous referring to you have something other than 0 on the right-hand side. Sometimes you see the same language used in a linear algebra context as well. An equation of the form ax equals 0 that would appear when you're studying null space is sometimes called a homogeneous equation. And ax equals b, where b is anything other than 0, is sometimes referred to as a non-homogeneous equation, just matching the language used in differential equations. That concludes today's video. In today's video, we practice writing the null space of a matrix as a span of vectors. The null space of a matrix can be found by setting up the augmented matrix corresponding to the equation ax equals 0, and then using row reduction to solve that matrix equation. For some matrices, when you look at the null space, there will only be one vector inside of it, which is the zero vector itself. But if you have another matrix, for example, if you have a rank deficient matrix like this one, you might find that the null space contains more than one vector inside of it. If you're in a situation like that, our process is to take all the variables in the system, and express all of the variables in terms of the free variables. Express everything in terms of the free variables, and then write your solution as a linear combination: free variable times vector, free variable times vector, free variable times vector. That allows you to describe the null space of A as a span of vectors. The Rank-Nullity Theorem gives us a relationship between the dimension of A's domain, the dimension of A's range, and the dimension of A's null space. Specifically, the difference between the dimension of domain and range is equal to the dimension of A's null space. And this comes from the fact that the columns of A fall into two categories: the ones that are actually needed to construct A's outputs, what we call the pivot columns of A, and the sort of extra or redundant columns of A that correspond to free variables. The pivot columns tell you the dimension of the range, and the free variable columns tell you the dimension of the null space. Once you have found the null space of a matrix A, you will see that null space appear in matrix equations involving A, even if on the right-hand side you have a non-zero vector. Solutions to non-homogeneous equations like this one usually show up in the format of the null space of A plus some other additional vector.